All right, welcome to our review class for the exam, chapter 16, 17, and 18. And today I'm broadcasting from Tacoma Park. I'm at my office. So first of all, can you see the screen? Can you see the slide?
Yes.
Okay. If you can't at any time, just let me know. All righty. So this chapter was involving solubility and complex ion equilibrium. And as we saw, solubility of slightly soluble substances involves equilibrium, and so we get another type of equilibrium constant, which is the KSP. All right, now, just to point out this slide, this is slide number 8, and you need to make sure you have these memorized. Okay, so you can look through that. Slide 9. Now, silver chloride, Ag is silver. We've always talked to it as insoluble. It does form a precipitate. However, as we saw, that's an oversimplification, and actually a very small degree of it does dissolve. And now we're going to keep track of that because it does have an impact in various ways in industry and pharmacy. And so that's why we give it such importance. Okay, so some terms on this slide, slide 12. Solubility, you should know what that means. How much of a salt will dissolve? Even insoluble compounds have very slight solubility, so a tiny amount does dissolve, and that's going to involve equilibrium. Okay, so we're focusing on the part that does dissolve. And now you asked a question about KSP, so let's look at what KSP is on this slide, just to review. It's an equilibrium constant. Now, in this case, we don't have a chemical reaction, but what we have is a solid here. Pb remembers lead chloride, and when it dissolves, it forms a lead ion and two chloride ions. All right. Now, we can think of this like a reaction. Notice it's at equilibrium. So we're going to have an equilibrium constant, but we give it a new name, solubility product. Why? Because when we write the equilibrium expression, we take the concentration of each product raised to a power equal to their coefficient. So this is a coefficient of 1. This has a coefficient of 2. But as you remember, solids don't go in the equilibrium expression, so we can just put 1. And essentially, we just have a product of the two concentrations of the two products, each raised to the power equal to their coefficient. So we just get, there's no denominator, and that's our KSP. Stop me if you have questions. Okay. So the first thing you have to be able to do is know how to write a KSP expression. So if I give you this equation right here, by the way, can you see my pointer?
Yes.
So if I give you this equation, I say, okay, what's the KSP expression? You just take the concentration of each product raised to the power equal to each of their coefficients. Since they're both 1, we don't have to write the 1. Okay, so make sure you know how to do that. And let's go to 16. And these are just some other examples you can look at yourself. So given the equation, the equilibrium equation, write the KSP expression. So should be fairly easy. Oops, I didn't want to do that. What did I say? 19? Oh, that's 19. I think I wanted 20. Yeah, I wanted 20. Let's try 20. Whoops. What did I do? Oh, well. So there's 3 types of equilibrium problems. I think I got my numbering mixed up. Let's see, type. That was 20. That's 21. Well, let's see. Okay, well, let's see if we can find. Yeah, this is what I wanted to do. 23, actually. Okay, anyway, we're on slide 23. And Michael, you asked me about equal KSP problems. So this is one type. So what we're going to do here is write here we have the equilibrium equation. All right, so we set up an ICE table. Remember, I is initial, change, and E is equilibrium. So let's say, and it tells us that we're given 2.0 times 10 to the minus 4 molar for the concentration of copper 1 bromide. Okay, so that's the solubility. So if I put this into solution, that's how much it's going to dissolve. Before I put it in, there is zero of those ions, 0 of those ions. That's the initial. What's the change? Well, we're saying that this much dissolves. So if that much dissolves, for every one of these dissolves, we get one of these and one of these. So for the change, it's 2 times 10 to the minus 4. It gains that much, and plus 2 times 10 to the minus 4. So what's the equilibrium concentration? Well, we don't have to pay attention to the solid because the solid is not in the equilibrium expression. So it's 0 plus that, and we get 2 times 10 to the minus 4. Same thing here. Here's our equilibrium, our KSP expression, concentration of Cu times concentration of Br. And these are the equilibrium concentrations. So we just plug those in, multiply them together, and that's our answer. So in that type of problem,
So for a problem like this, basically, instead of doing automatically, you just square the solubility.
right. However,
You can't always do
if
that, but just
if
specifically
if
for this.
right, exactly, you're exactly right. But like if this coefficient was 2, then you'd have to square this one, right? So it depends on the coefficients. Since they're both 1, then you just the exponent is 1, the exponent is 1. Do you see what I mean, Michael? Okay, let me show you the next one. Let me show you the next slide. See this slide, this is what I mean. So see right here, you'd have to put an exponent of 2 there because coefficient is 2, exponent of 3 there, and the coefficient is 3. And then you'd also have to double and triple the amounts because of these coefficients.
So if you're already like multiplying, like if you're already squaring the concentrations, why do you have to double and triple them if you're already squaring them?
Okay, good
Either
question. Good question. So first of all, the squaring and tripling, that's part of the KSP formula. And you know how to do that because if the coefficient is 2, are you hearing me okay? If the coefficient is 2 and the coefficient is 3, then the exponent will be 2 and the exponent is 3. So you know that part. Now, you just have to think through what's happening when you dissolve this baby. When you dissolve one of these, you get 2 bismuths and 3 of those. So if this much is going to dissolve from the starting compound, well, you're going to get twice that much dissolve and 3 times that much dissolve based on the coefficients. So the coefficients come into play 2 times.
so what's the final answer? Is it
So the final answer would be you would take 2 times 10 to the minus 15 squared times 3 times 10 to the 15th cubed. I think the final answer is in the next page. Let's see. Whoops, it's stuck. Let me try this. There you go. And there's the final answer. Huge number. And actually, you can put it in standard form like that. But anyway, does that answer your question, Seacom?
yes, thank you.
Okay, Micah, does that help? Just try
Yeah.
to, try to look those over. There's some other problems you can look over. All right, now we'll go to, whoops, I got my numbering messed up. How did I do that? Wait a second. Oh, that's what I wanted. I got my numbering messed up. Oh, well, that's okay. So now the type 2 problem, we have to find equilibrium expressions. So here's an example of a type 2 problem. Let me go through it again. The type 2 problem, you're given the KSP, and they say find the equilibrium concentrations and find the solubility. So how much will this dissolve, and how much of these ions will be around at equilibrium? So we set up our ice table. We don't know how much is going to dissolve. We're starting with 0 dissolve, 0 dissolve before we put it in. Once we put it in, a certain amount of this dissolves. And whatever amount of this dissolves, since it's a 1-to-1 ratio, that means we'll get the same amount formed of each of these, X and X. And then when we go to our KSP expression, we write this out, and we're not concerned about solids because they're not part, so we ignore this. Solids don't come into play in this KSP expression. So then we just put an X there and an X there, and then we get X times X, and this is given 1.8, and then we have X squared, and then we solve for X. Now once we find X, that X, that tells you how much of this dissolves, but it also tells you at equilibrium the concentration of each of the ions, which are all the same. So that's a type 2 problem. Oh yeah, good. Okay, so this is just a reminder, slide 38, which is solubility is the amount of the substance that dissolves, and insoluble solids dissolve a very, very tiny bit. So that's something we already looked at, but just a reminder. And then we go to the type 3 problem. Whoops. Wait a second here. Did I do 42? Oh, I got my slides messed up. Mixed up now. Thing is, I can't minimize because otherwise, I think I did this one. Yeah, let's just do this one. We'll do this one here. Okay, so the type 3 problem. Let me say that's not a good one. Let me do another one. Let's go back. Sorry about this. Thing is, if I minimize, it will it won't let me minimize because I'm picked out the one I wanted to do. Oh well, let's see which one it is. This one, not that. Yeah, this is the one I wanted to do. Okay. This is the one I wanted to do. Okay, so what do we have here? Well, remember this concept of Q, which is a non-equilibrium situation. And we're going to compare Q with K. So here we have these two solutions. Here's our equilibrium. Here's our equation showing the ions dissolve. The KSP would be, which is the same as the Q, but the Q just means it's not at equilibrium yet. So giving these concentrations, we fill these concentrations in just like we would in a KSP. AG has that concentration, CO has that. Everything's the same as KSP, but it's not at equilibrium, so we call it Q, just quotient. It's 1.10 to the minus 8. Now, since that is bigger than the KSP, because the KSP is given up here, if the Q is bigger, than the KSP, it means you have too many of these. And it's not at equilibrium yet. So how will it reach equilibrium? It'll shift left, and it shifts left. That means it's going to go toward the solid phase, and precipitation will occur. So the point is that if Q is greater than KSP, precipitation will occur. It'll shift toward the reactants left, which is basically the solid, the starting material, the solid, which if it's a solid, then it's a precipitate, okay? And then just the opposite would occur if Q is less than K. Then
Can you go over another one, please?
oh, sure, I can go over another one. Let's go over another one. Let's see here. Let's go over another one. Yeah, we'll do this one. Let's do this one. This is also precipitate. Oops. That doesn't matter. It's the same idea. Anyway, okay. So here we have this solid breaking up into these ions. And when we write the KSP expression, it would be this. We call it Q because it's not at equilibrium again. So I'm plugging in the values that are given, that we're starting with. It tells us what the concentrations are up here. So when we calculate Q, it's 10 to the minus 10. How does that compare with KSP? Well, it's 5.3 times 10 to the minus 10, 3.2. Whereas KSP is 1.9, which is bigger. 5.32 is bigger. And if Q is bigger than KSP, that means there's too many products, so it's going to shift left and precipitate. So when Q is greater than KSP, it's going to form a precipitate. And I have other examples in the slides. Any other questions on that? Okay. All right. Then after that, we go to complex ions. And the reason we go to complex ions, because first of all, they exist, but number two, they also are going to involve equilibrium. So this is a term you should know. What's a complex ion? It's a charged species made up of a central metal ion surrounded by things that are attached to it called ligands. M stands for the metal. And also the ligand happens to also be a Lewis base, means the Lewis base, that concept means whatever donates electrons is a base, so it's a Lewis base. And here's a definition of a ligand. You should know this. An ion, an atom, or a molecule having a lone pair of electrons that can be donated to form a bond with a metal. So each of these L's are attached to the central metal ion, and they're called ligands. Okay, so that's another example. It's called a complex ion because it's a very large ion. It's complex. It has a charge, positive or negative overall. You have a central atom, and then you have substances that are attached to it. In this case, it's H2O in every case. Okay, you should know that the terms on this page: a ligand, a neutral molecule, atom or ion having a lone pair of electrons that can be donated to form a bond with a metal cation. Okay. It forms a coordinate covalent bond. It's called coordinate covalent because it supplies, one of the atoms supplies both the electrons in the bond, which is very unusual. So this is a bond where both electrons originate from only one of the two atoms. And remember what the coordination number is. It's the number of ligands. So if I were to give you this on the exam and say, what's the coordination number? Can you see that it's 6? 1, 2, 3, 4, 5, 6. So the number of atoms or atoms or molecules or ions attached, each of those is a ligand, and the number attached is the coordination. So that hopefully should be very easy for you. Okay, now here's why we even talk about complex ions in this chapter. Because when you form complex ions, it involves equilibrium. So we have another equilibrium constant, we put K sub F. So it's either the formation constant or stability constant, but it's how these babies are formed. So like in this case, you got 4 ligands attached to this guy and you form the complex ion, but it's at an equilibrium situation. And all the ions are aqueous, so they're all going to show up in the equilibrium. So this is just another equilibrium constant. Okay, let's see here, 62. So instead of breaking apart, we're putting something together and forming the complex ion. Could one of you tell me what's the coordination number of this particular complex ion? What's the coordination number of that?
6.
6. So very easy. You got it. That's easy. Coordination numbers are easy. Got it. Good. And just one other point from here is that it occurs in steps. So you add one at a time. I'm not going to make a big deal about that. Okay. So those are the highlights from chapter 16. Now what I'm going to do is stop the share. And oh, we have Delilah. Hi, Delilah. We have Delilah now. And now what we're going to do is go to the next chapter 7. Let's see. We just did 16. Which one is 17? 17. There we go. And now we'll do 17. Thermodynamics. Okay. So can everybody see the screen? All right.
Yes.
Good. Okay. Whoops, I have a chat here. Let's see. Yes. Good. Okay. Thank you. Good. So there's a lot of terms in this chapter that you need to know. So let's go over some of them. Definitely, you want to know the definition, study of energy changes that accompany physical changes in chemical reactions. As we'll go over the 3 laws of thermodynamics. Remember what a state function is. It only depends on the initial state and the final state. So internal energy, enthalpy H, entropy S, free energy G are all called state functions because they don't depend on the pathway, remember? Okay. Okay, remember this one. This is easy too.
Wait. Quick question. So if Q is equal to the KSP, that does mean the system is at equilibrium, correct?
Yes, yes.
Okay.
Very good, very good, very good. Yes. If Q is equal to KSP, it's at equilibrium. Right. Very good. So remember what a system is. It's the part that you're focusing on, you're studying. The surroundings would be, everything else, all the universe except the system, and the systems and the surroundings together would be called the universe of study. And with that model, we can study things flowing in and flowing out, heat or work or whatever. So again, you should know these terms. System is a part of the universe under study. Surroundings, all of the universe except the system, and the systems plus the surroundings equals the universe. Not the real universe of the world, but just the universe of study. Okay, does that make sense? Because we're not studying all the galaxies and stars and stuff like that. Okay. Okay, in this one, I only want you to know for enthalpy that it's the heat content of a system. We could think of enthalpy as heat. And spontaneity, remember that what that word means. Spontaneous occurs without a continuous input of energy. Once started, it continues on its own. Like once you push a ball, then it's going to start rolling down the hill, around the hill. Okay, it's another. Not requiring an outside source of energy to proceed. So it occurs without a continuous input of energy. And as we mentioned, most, but not all, exothermic reactions are spontaneous because there's another factor involved. And remember, has to do with enthalpy and temperature. Well, two other factors, I should say. Okay, then we get into entropy. So it's disorder, chaos, spreading out. And that little memory device I gave you, this is now slide 12. Just think of the S in disorder. And actually, S was actually named after a person, just like one of your discoveries will be named after one of you. The mica principle. What do you think? I like it. And anyway, S is a symbol for entropy because E was already taken for energy, so they had to come up with another letter, so they call it S. Disorder. You should know that entropy is a measure of disorder. Another definition is Gibbs free energy, the amount of energy that is available to do useful work. Gibbs free energy. Okay, then we get more into entropy. So it's disorder. Like if you don't pay attention and put in effort, what happens to your room? It becomes very messy. Solids. Well, as you go from solids to liquid to gas, you're going toward more disorder. They're spreading out. Solids very ordered. A gas is not. It's all over the place. I like my hair in the morning before I comb it. No, just kidding. All right. Let's see. So here we say that chemical reactions and phase changes naturally tend toward disorder and higher entropy. Then we get into the rules for entropy, and you should make sure you look at these because you'll be asked to compare different things, which has more entropy. So like first rule, gases have the most entropy and solids have the least entropy because they're very ordered. So aqueous comes after gases and then liquids. The more atoms you have, the higher the entropy. Then the bigger the atoms, the more the entropy, the more the disorder. Rule number 3. Amorphous solid has more entropy than crystalline. So wax, diamond is very ordered, whereas wax is amorphous, doesn't have a structure. Rule 5, complex ions and hydrates are lower than the sum of the entropies of their components. So, So this is much more ordered because everything's connected together. Here they're apart. So this is less ordered, less entropy, more entropy, and this has less entropy. The greater volume you have, the greater entropy. Decomposition reactions lead to higher entropy. Reactions involving a greater number of moles have higher entropy. Reactions involving a greater number of moles of material and more random physical states have more entropy. So you can look through these rules. Okay, good. Okay. So here's a type of question. In each of these cases, which has more entropy? Well, when an alcohol is evaporating, it's going from a liquid to a gas, so entropy is increasing. We can say plus S, or we could put an upward arrow. When a solid explodes and it becomes a gas, it's going from very ordered to very disordered. So there's an increase in entropy. Perfume spreading out through the room, increase in entropy. But water freezing, decrease in entropy. Why? Because when it freezes, it forms a very orderly pattern. So there'll be questions like that, comparing one to the other. And then we get into the 3 laws of thermodynamics. So you should know these 3 laws. The first one you already know by another name. The first law of thermodynamics is that the law of conservation of energy. Energy is neither created nor destroyed. Okay? The energy of the universe is constant. The second law, in any spontaneous process, there's always an increase in the entropy of the universe. So entropy always increases in the universe. And the third law, the entropy of a perfect crystal at 0 degrees Kelvin is 0, no motions. Okay? So you could see a multiple choice question. Which of these is the second law of thermodynamics? Then you got to pick it out. Okay? It's just a matter of memorizing that. 40. Okay, now this is a good example of using this equation. You'll be given this on your reference page. You just have to know what it means, but it's really easy. Just have to be careful doing the math. So what this means is, for this reaction here, you take 2 times the value of this product plus 2 times the value of that product, and then you add them together. That's here. Minus, because that's what this template here means. And then you just take 2 times the value of this reactant, 3 times the value of that reactant. And that's what you have here. And then the values of the reactants and products are here, so you just plug them in, you add them, and then do the subtraction. Okay, so do you think you could do a problem like that? It's not hard, it's just being careful with the math. Okay, then we get into enthalpy, which is the heat of the reaction. And this is going to be another driver of reactions, and it's going to be a factor in determining whether something is spontaneous or not. Okay, so on this slide here, it's an interesting slide. Exothermic delta H is negative, energy is released. Usually spontaneous, but not always. It moves to a lower energy state. You light a candle, it continues to burn. Processes tend toward lower energy. But then endothermic reactions, delta H is positive, energy is absorbed, tend to be non-spontaneous, but some are spontaneous. And then I talk about ice melting and evaporation. And when we come to the conclusion that temperature is also a factor here, remember we talked about that, and then we get to the big equation, which includes, well, I think, wait a second. Well, the thing I wanted to say was that turns out that whether or not a reaction is going to be spontaneous depends on 3 factors: entropy, enthalpy, and temperature. And then we got this equation, right? There's our fanfare equation. Delta G equals delta H minus T delta S. And if delta G is negative, it's spontaneous. And it depends on what the other guys are. This little 0 here, you should know, there'll be a question on that. That means it's standard conditions. 1 molar, 25 degrees Celsius, and 1 atmosphere pressure in 1 molar. Okie dokie. This was a huge discovery by Mr. Gibbs. Now, here's a type of question you got to be able to answer. Well, actually, before I get to that, I should say is, so if delta G is negative, spontaneous. Delta G is positive, not, and if delta G is 0. And remember, Michael, you just asked that question. Again, you ask great questions. So when we're talking about Q, if Q is equal to KSP, it's at equilibrium. Now here we're going to say when delta G is 0, it's at equilibrium. And then let's see if I have this mathematics land. Oh yeah, just to say that these equations will be on the reference page, and they're all done the same way. So if you understood what I just did for the delta S problem, then you could do any of these. In case I can't remember if there's one of each of these or not. And then we're going to go to mathematics land. And so there will be a question involving this. And you have to think. When all else fails, think. So this is, we went through this. So if I say to you, if delta H is negative and delta T is positive, regardless of the values, the actual values of any of the things, and also including values of the temperature, when you take a negative number minus a number, it's always going to stay negative. So delta G will always be negative. So it's spontaneous. And then I went through the next case. What if delta H is positive and delta S is negative? Well, it doesn't matter what the values are and what the temperature is, because when you take a positive number minus a minus, that's a positive. So it's always, the sum is always going to be positive. And if delta G is positive, not spontaneous. And then in the other two cases, which you can go through, it depends on the temperature, which will be bigger. And I went through the same thing on the next page just to show you the same thing. So you should be familiar and understand this page. Okay, let's go to 70. And then this sort of is a good summary. So if delta G is negative, spontaneous. Delta G 0, equilibrium. Delta G positive, not spontaneous. And then we get into this whole thing. The relationship between delta G and K. So when delta G is negative, spontaneous, K is big, favors products. And you can look through the other points there. This equation I will give you, you could possibly have a problem where one of these variables is unknown and then you solve for it. Let's see. Oops, that's too fast. 76. There you go. So this would be a case where one of the variable here, you're just using this equation and everything is known but K, and then you can solve for it. So I go through that. So that's what I wanted to review for that chapter. And now we're going to go to 8. Whoops, wait a second. I didn't stop the share. That wasn't good. Supposed to stop the share. Let me go to, here we go. Can you see what I have on the screen?
Yes.
Okay, good. Okay, and I'm going to keep this to an hour, so we're in good shape. Okay, so electrochemistry, electrons on the move. So we're actually focusing now on electrons. Very important. Make sure you know this. What is the definition of electrochemistry? There's a question on this. It's the study of the interchange of chemical and electrical energy. And it's going to involve oxidation and reduction reactions. And electrons are going to be on the move, which is going to produce our electric current. Okay, so an acid base, reactions, we focus on transfer of protons according to Bronsted-Lowry approach. And oxidation reductions, we're looking at electrons. And our memory device, oxidation is loss, reduction is gain. Oil rig. Oil rig. Okay. Very important that you have this memorized. Oxidation is the loss of electrons or an increase in oxidation number. Reduction is the gain of electrons or a decrease in oxidation number. All right. Oops, did I just do? Oh, I know what happened. You need to know these oxidation numbers. You have to memorize these, but they're not hard. And this little thing here helps you remember. Those in this column are always +1. Oxygen's always -2. And the halogens are always -1. Whoops, always -1. And then, let's see, 10. And so a type of question you might see, I might say, what's the oxidation number of P? Na is in column 1, so it's 1. So you have 2 of them, so that's +2. Hydrogen is 1. You have to memorize it's always 1, and oxygen is always -2. So if you take 3 times -2, you get -6. And then over here you've got 1 plus 2 is 3. So to make that add up to 0, P has to be +3. So you need to be able to, like in this case, I might ask you, okay, what's the oxidation Mn? You know that this K is always +1, it's in column 1, and this is always -2, but you got 4 of them, so it's -8. So this has to be 7 then. Okay. Then I went through balancing an acid-base a complicated redox reaction. Now, the good news is I'm not going to ask you to balance the entire thing, but I may ask a question related to it. So here we're just showing the ions, a redox reaction, and we want to balance it. So first thing we do, we break it up into the 2 half cells. So this is 1 half cell. And here we have oxidation, electrons lost, and it's completely balanced already. Then over here, we have, this is where the reduction takes place. Now, in this particular case, we've got 2 chromiums there. So we have to put a 2 there to balance that. We have 7 oxygens over there. So to do that, we're going to add 7 H2Os. And then we need to balance the charges. So 2 times +3 is what? Is +6. So we only have a -2 here. So how are we going to balance the charge? Actually, skipped a step there. Let me show that again. So we got to this point to balance the hydrogens. And by doing that, we had to add 14 H pluses. Then when we come to this slide, we've got 14 pluses and a -2. So that's going to be +12. And here we have 2 times 3 is +6. So to balance it, we're going to add 6 electrons. So we can balance the positives and negatives. So this now the charges add up to +6, and that's +6. But since the number of electrons, just like on the quiz, number of electrons gained have to be equal to the number of electrons lost, we have to add a 6, multiply everything by 6. And then we add the two equations together, cancel the electrons, and that's our final. And then there's a couple extra steps when you're talking about balancing in a basic solution. But what I want to get to is the galvanic cell. So let's jump to galvanic cell. So what happens in a galvanic cell? Chemical energy gets converted to electricity. So we're generating electric current. People had trouble with that on the quiz, but it's called a galvanic cell or voltaic cell, either way, and it generates current. And so that's going to be our battery. If I want to do 38, hold it. Okay, yips, yeah. So galvanic cell, device in which chemical energy is changed to electrical energy. It's a spontaneous redox reaction, and it can do work. It can operate your electronic device, which is your battery. Okay, so remember, this is called a voltaic cell or galvanic cell. Chemical energy is being converted to electrical energy, right? Oxidation occurs at the anode. Here's the anode. Reduction occurs at the cathode. Here's a cathode. A memory device. These are both vowels, O and A. So I said, what occurs at the anode? Oxidation and reduction, oxidation. What occurs at the cathode? Reduction. They're both consonants. I can put that there. So what's happening here? Zinc is giving off 2 electrons and it's being oxidized. So this starts to get eaten away. The electrons that it gives away flow through the wire and are absorbed over here in this cell. And those electrons get picked up by the copper ions and they get reduced. And this starts growing. And so you're producing a current or electric current. And if you didn't recharge the battery, then eventually it would stop because all the material would be used up. All the zinc would be used up. So electrons flow from the anode to the cathode. And that's what I emphasize on this next slide, this one. So it's spontaneous. As soon as you connect it, it starts flowing. What is this thing here in the middle? It's the salt bridge of the porous disk. It allows charge balance. So the negative ions that are in solution move this through the porous disk or the salt bridge. Because otherwise the electrons would build up and it would stop. Because electrons would repel each other. If they're not being absorbed, they would repel. So the negative ions have to go through here to balance the charge. So electrons flow from the anode to the cathode in the galvanic cell or the voltaic cell, which is basically what a battery is. And then we have the shorthand. It's easy. This little double line here is salt bridge. This is the oxidation cell. Zinc is the anode. This is reduction cell. And copper is the cathode. All right. Then we got into this table, which it's something that we're going to use to determine the voltage between 2 cells. These are all put as reductions just to save space. So they're all gaining electrons. Reduction is gain, oil rig. So this would have the greatest tendency to be reduced. And then down here, it has a very little tendency to be reduced. So the opposite way is what it favors, which would be if you reversed everything and you went this way, you would change the sign. And then we're going to use that to determine voltage. Let me go to 51. Okay. So by convention, electrode potentials are written as reductions. When pairing 2 half cells, you must reverse one reduction half cell, the lower one on the list, and then add them. Okay, so a couple problems. Let's see here, or this problem here. So the question is, and here I have 2 half cells. Question is, what's going to be the voltage when I connect them? It's actually going to be silver in one cell and iron in the other, but all you have to do is you change, since whichever one is bigger, you don't touch the lower one. You're going to change the sign, which make this a negative, and add them, and this basically is going to go the other way. It's going to be oxidation. So that's all you have to do. So it's actually quite easy. You just have to, whatever is lower on the table, you change the sign and add them, and that'll be the voltage. And it doesn't matter how many electrons are involved.
Are we gonna have a lot of questions like this? Or
No, maybe one question.
Okay.
One question. Now, the cell potential, the voltage has to be positive. This you can put as E or just V as in voltage. This is called cell potential or voltage. It has to be positive because it's not going to operate if it's not. And then we started comparing. And don't get nervous about this. All I want you to know is that they're all connected. That free energy, equilibrium constant, here we're lazy, we don't put the EQ, and the cell potential or voltage are all connected. And they each have an equation connecting them, but don't get nervous, it doesn't matter. I'm not gonna, just want you to know that they're all connected to each other by those equations. Okay, then we want to be able to compare the three of them. So if delta G is negative, K is big, positive voltage, spontaneous. At equilibrium, delta G is 0, K is equal to 1, and the cell potential is 0. And if delta G is positive, it won't be spontaneous. K will be very small. And the voltage will be negative. You can't have negative voltage. It's not going to, so basically it means it's not going to work. Nothing happens, non-spontaneous. Okay. So for any galvanic cell to operate, delta G must be negative, and the voltage or cell potential E, and I apologize for that, but that's unfortunately they use both. They use cell potential or they use voltage. So if they use cell potential, they put an E. That little 0 means standard conditions, 1 molar, 25 Celsius, 1 atmosphere. But if it has to be positive, you have to have a positive voltage, otherwise it's not going to go. It won't operate. Okay, and then this one here. So we've been working at standard condition, but what happens if you change the concentrations to make it more than 1 or less than 1? So like in this case, we're using 2 molars. So if that's 2 molar, it's a stress on the system and it wants to consume or replace. So it's going to shift left. When it shifts left, the voltage will be less than that. Over here, the Mn is more than 1. Mn is a reactant, and so it's a stress on the system. It's going to consume or replace. So in this case, it's going to consume it and shift to the right, so the voltage will be higher. So it's just Le Chatelier's principle. Once again. Then we have this one weird case where what happens if you have the same material in both, the same electrode, silver, and you change the concentrations? Well, if you do that, it's called a concentration cell, but the voltage will be very small. And I suppose it has some applications where you want to have a small voltage for a process. But so a concentration cell just means concentrations are different, but the electrodes are the same. So that's just memorizing what that means. And then 74, just the point of that is, oops, sorry, that's the wrong one. Not so fast. There are different types of batteries, but they all work on the same principle. In one cell, you are losing electrons, and in another cell, you're gaining electrons. In other words, it's a redox reaction. and it works with different materials. I'm not going to ask you the different kinds of batteries, just to give you examples. And as I pointed out, this lithium ion one is really important today for computers and phones and electric cars. And 75, whoops. This one, just to know what a fuel cell is, it is a type of battery or galvanic cell, and the reactants have to be supplied continuously. So that's all I want you to know about that. But then we have an unwanted redox reaction, rusting or corrosion. It is spontaneous. It actually produces an electric current when rusting occurs. It's actually a redox reaction. So rusting and corrosion is unwanted, but it is a redox. It does involve oxidation and reduction. Now, gold, one of the reasons why it's so valuable, and the same for platinum, they don't oxidize, and so they don't rust, just to know that. Gold and platinum do not corrode. I think you probably know that. And that's why sometimes you give a wedding ring, because the idea is a marriage is going to be lasting. And so gold is lasting. It'll never corrode. Okay, let's see. Next one. Just to point out that rust does involve redox. You don't need to know the specifics about that. Oops. Now, and then some substances form a natural coating to prevent corrosion. So aluminum forms a coating. Some metals tend to develop a thin oxide coating. So aluminum forms aluminum oxide. Copper forms copper carbonate. It's sort of a greenish color and it won't corrode. And silver tarnishes to form silver sulfide. So another way you can avoid, that's 78, 80. We did that already. Oh yeah. So you paint it. You paint something. You paint your bicycle. And if it gets scraped, then it might start rusting. Another process is galvanize. Remember what I said. A way to remember galvanize. Think of Z with zinc. So it's a process in which steel is coated with zinc. It's said to be galvanized. Another way to prevent corrosion is, besides painting it or galvanizing it, is to make an alloy, combine it with another metal. And in this one here, the next slide, which I meant to say 83, let's see. Nope. Oh, that's what I wanted to show. So in this particular one, it's called a sacrificial anode because it gets sacrificed. Magnesium has a greater tendency to be oxidized than iron. So if you attach a magnesium rod, it'll corrode, but the iron won't. It's kind of cool. It has a preference to be oxidized. So that's another way to prevent corrosion. And then we get into electrolysis, which just means adding electricity. We're almost finished. I should be finished in another 5 minutes. So it requires current. And so look at this slide 84. Everything's opposite. This is how you charge a battery. You add the current and everything gets reversed. So everything is in reverse now. And if there wasn't evaporation or corrosion or loss of materials, the battery, if you kept recharging it, it would last forever, but it doesn't because of leakage and corrosion and evaporation. But remember, oxidation, regardless of whether it's an electrolytic cell, that is a cell you're adding electricity to, or galvanic cell, a battery, oxidation always is at the anode, reduction at the cathode. Okay, 6. And just know that water, using electrolysis, you can break water up into those two, hydrogen and oxygen. You can separate it into its elements. And the same thing for salt. NaCl, by passing electricity through it, first you make it molten, and then you pass electricity through it, you get a redox reaction. You don't need to know the specifics of the redox reaction, just to know that it's a way to separate it into its component elements, chlorine and sodium. But once again, at the anode, you have oxidation, at the cathode, reduction. And another cool thing you can do with electricity is you can electroplate something like a spoon. If you want to get a silver spoon, you can use electricity and connect it in this way with a silver anode, and the spoon will be coated with silver. And of course, with electricity, it's how we charge batteries. We use electrolysis to charge batteries. And then only a couple more slides here. So we should know Coulomb is a unit of charge. An ampere is 1 Coulomb per second. We can write it this way. And this will be given to you. This is a constant, 9.65 times 10 to the 4th coulombs per mole. So I went through this one problem here. So you should go through this again. Basically, we're given mass, and we want to find out the current. Current is basically coulombs per second. So this is given, and we have the atomic mass on the periodic table, 52. So we're given 0.86 grams. So we're going to convert that into moles. And we know that from this equation, for every mole of copper you get, you need 3 electrons. So it's 3 moles of electrons per mole. But then we know that there's 9.65 times 10 to the 4 coulombs per mole. So we just multiply by that and then divide by time. So putting in the numbers, we have the mass, we divide by the molar mass, we get the moles. We have 3 times the moles of electron, but we have to multiply this by 3 to get the number of moles of electrons. Once we get the moles of electrons, so we multiply this by 3, we get that. And then we multiply this by this conversion factor, 9.65 times 10 to the 4 coulombs per mole. Electrons cancel and you get coulombs. And then, but an ampere is coulombs per second. Well, we're not given seconds in the problem, we're given minutes, but so we just have to convert it to seconds. Basically, we multiply this by 1 minute over 60 seconds. Let me get the answer. I'm not going to ask you a full problem, but I might ask you something related to something like that. And then this is going to be, these are the review notes that I gave you last class. And the reference page on the exam is going to have that. Okay, so that's a quick review. I mean, in general, what I always say is, know everything in the PowerPoint notes, know how to do each kind of problem, and know all the terms. All right, so let me just stop the share. There I am again. Congratulations, you made it through. Any other questions or concerns at this point? I really want you to do well. So do your road work tonight. And I am also available to answer any other questions you might have tonight, today or tonight. Just send me an email, and tomorrow morning I always come in, and I will be here early. What time are you going to come, Micah?
I'm honestly not sure, but it will be before class starts because
Okay.
Dr. Perez told us that he's gonna give us a review for our final exam,
Right.
and then he's gonna let us leave early
Right.
so that people can go get ready and so that the chemistry students can go take their exam. So it'll probably be before 10. I thought he was gonna talk to you and give you a
He
time,
did.
but I guess
No, he
didn't.
did. I would say, well, put it this way. I'm going to be here at 8 tomorrow. So what time does your biology?
Okay.
You're going to leave your biology class early? Is that it? I mean, you could come at 9:30.
Yeah, that's what he said today.
So come at 9:30, and I'll be down here
Okay.
in the office. Okay, I think there's 3 of you that are going to do that. So come to the office,
Okay.
and Okay? Anything else? All right then. This is Professor Coppola signing off from Tacoma Park, Maryland. Goodbye, everyone. Bye-bye. See you tomorrow. Good luck.
That's funny.
Yep. Bye.